Alright, so you see I am continuing with this motivation for Zalcman's lemma, alright, and so let me recall what we were doing. So let me use a different color. So basically you are trying to understand you know, the behavior of a normal family at a point, okay. That is understanding that is the, you know, the key to understanding the statement of Zalcman's lemma, okay. How does a normal family of meromorphic functions, how does it behave at a point, at a given point? So you know, the important outcome of this analysis is that, you know, you can characterize normality at a point, and normality at a point is defined as normality in a neighborhood of that point, in some neighborhood, open disk surrounding that point, okay. And then so you see, this means that normality can be defined locally, and it is in fact a local property like analyticity, okay. So we start with the family script f. These are meromorphic functions defined in a neighborhood of the point z0. I am assuming the point z0 is in the complex plane. It could have been also a point in the extended complex plane, namely it could have been the point at infinity, okay. All arguments will work, but you will have to make the right modifications. You know how to do that because we know how to deal with the point at infinity and taking infinite limits and things like that, okay. So alright, so well, what I told you last time is that you start with this family script f, and what you can do is, given a function small f in script f, okay, you want to study that function in a neighborhood of the point z0, okay. So what you do is that, you know, you take this neighborhood of this point, which is actually it's a disk centered at z0, radius rho, okay. You take this neighborhood, and I am also assuming that the boundary of that disk is in the domain where the functions are defined, okay. So and the reason why I am including the boundary is because I want a compact set, okay. The disk along with the boundary forms a compact set. It is a closed and bounded set, okay. And well, so suppose I want to study a particular function small f in the family script f at its behavior very close to the point z0, then what I do is I zoom into the point z0 and try to study the behavior of the function. And how do I do this zooming? I do the zooming in this way. So I define this zoomed function here, okay, g. So given f, I zoom f to get a new function g, okay. And what is this zooming? You are zooming the function f centered at z0, and the zoom factor is 1 by epsilon, where epsilon is supposed to be a small positive quantity, so that 1 by epsilon is large. In fact, epsilon is to be taken less than rho, okay. And then you define this new function. This new function, which is for this f, you define this function g, which is a zoomed function. G is just you take f, look at its behavior in a small disk around z0, and then you zoom the behavior by a factor 1 by epsilon, okay. And so what you do is that so this is how the zooming is defined. The zoom function g of zeta is f of z0 plus epsilon zeta, which means that actually what you have done is you are actually translating z0 to the origin, okay, and then what happens is that this this whole disk centered at z0 radius rho along with the boundary translates to a disk centered at the origin with radius rho by epsilon, okay. So 1 by epsilon is the scaling factor, and mind you, you should think of it like this. Epsilon is small, so 1 by epsilon is large, so rho by epsilon is greater than rho, so you have actually zoomed, okay. And so the behavior of the zoom function is being studied here, okay, and in this disk, and well and I am calling this zoom function g. So this is a very simple thing, and the point is that the difference between f and g is just a it's a bilinear transformation. It's actually it is translation and it involves a translation, it involves a scaling, okay. So what you have done is you have taken the variable zeta, you have scaled it by epsilon, okay, you have multiplied it by epsilon, mind you, epsilon is a positive real quantity, and then you have translated by z0, okay. So the g and f are of the same type of function, okay. G is analytic if g is analytic if and only if f is analytic, g is meromorphic if and only if f is meromorphic, and whatever if g has a pole at a certain point, then f will also have a pole of the same order at the corresponding point, okay. So and conversely, so g and f are literally the same function except that you have made a change of variable, alright, but the point is that g is a close up look of f. It's you are looking at f very close in a neighborhood of z0, that's the whole point, okay. Now what you do is that this is what you do if you have a single function, but what you could have done is you could have done this to a sequence of functions. So the point is if I knew that this family script f is normal, then suppose you assume that the family is normal in this closed disk, which means actually it's normal in an open set which contains this closed disk including the boundary, okay. And suppose this family is normal, normality is the correct notion of compactness that we require. Normality actually means normally sequentially compact. It means that given any sequence you can find a subsequence which converges normally, okay. So converges normally means converges uniformly on compact subsets. So assuming that the family script f is normal and I want to study the behavior of the family at a given point z0, okay. So if I take a sequence fn in this family, then you, because of normality, you can find a subsequence fnk that will converge normally on this disk. In fact, it will converge uniformly on that disk because that's a closed disk, okay. Normal convergence means it is uniform on compact subsets, and this disk centered at z0 radius rho is it's a compact subset. And again at the back of your mind you should remember that this argument will work even if z0 is a point at infinity. The only thing is that if z0 is a point at infinity, you will have to think of this, you should write this disk if you want with the Euclidean metric, if you want with the spherical metric, or you must invert the variable and look at a neighborhood of 0, okay. So so you can deal with the case when z0 is the point at infinity also, okay. But in any case, given this sequence fn, I have this subsequence which converges normally, so let me call the limit function as f, and then we have already seen this. Whenever you take a normal limit of meromorphic functions, the limit is either identically infinity or it's meromorphic, okay. And now look at what happens to the zoomed functions. So if fn k converges to f normally, then the zoomed functions for the sequence will converge to the zoomed function of the limit, okay. So this is obvious, okay, because the difference is only the difference is just a change of variable given by a bilinear transformation consisting of a scaling and a translation, okay. So so this G and K's will converge normally to G, okay, and all this is happening, mind you, because your zooming factor is 1 by epsilon. It's all happening here. It's happening in this open disk centered at the origin, radius rho by epsilon, which is greater than rho, okay, and well, this is where it is happening. Now you see, the point is that whenever a family of meromorphic functions converges, then the family of spherical derivatives will also converge, okay. Now this is just saying that, you know, the taking the spherical derivative will preserve the normality, the convergence, and the normal convergence, okay. So f and k converges to f normally. So what will happen is that you will get this, which is that the spherical derivative of f and k converge normally to the spherical derivative of f, okay, and we already know that because f and k converges normally to f, g and k converges normally to g, alright, and therefore the spherical derivatives of the g and k's G and K hashes, they will converge normally to G hash, okay, and but the point is that, you see, the original family, that the family script f you assumed is normal. So this family script f is normal, and Marty's theorem tells you that that a family is normal if and only if the spherical derivatives are normally uniformly bounded. Okay, and since we are already looking at a compact set, okay, there is a uniform bound for all the derivatives, the spherical derivatives of the functions in the family. Mind you, you have to use spherical derivatives because the functions in the family are not analytic functions; they are meromorphic functions. So you can't talk about a usual derivative at a pole, okay, but then you can talk about spherical derivative at a pole. So by Marty's theorem. Marty's theorem, mind you, tells you that normal sequential compactness is equivalent to normal uniform boundedness of the spherical derivatives, okay, and it is a generalization of the Montel's theorem for analytic functions, which says that the normal sequential compactness is equivalent to uniform boundedness, normal uniform boundedness of the original family, okay, and but the point is, when you go to Marty's theorem, you go to from the uniform boundedness of the normal uniform boundedness of the given family, you switch to the normal uniform boundedness of the family of spherical derivatives. Okay, that is a quantum jump that you make from Montel's theorem for analytic functions to when you go to Marty's theorem, which is for meromorphic functions. So there is this uniform bound M, which works for all functions in the family script f. So it will work also for these f and k's. It's a bound for not the functions, but it's a bound for the derivatives, okay, the spherical derivatives. So all the spherical derivatives of the f and k's are bounded by M, and then, well, what happens is, therefore, now if you take the limit, so there is a chain rule that's working here. There is a chain rule. The spherical derivative of the zoomed functions g and k hash is epsilon times the spherical derivative of the f and k. The spherical derivative of the g and k's is epsilon times the spherical derivative of the f and k's, because this. So the the idea is that you're zooming by a factor 1 by epsilon, okay, you're going closer to the point you're zooming into the point by a factor 1 by epsilon, okay, but then the spherical derivative becomes smaller, okay, the spherical derivative gets multiplied by the factor epsilon. Mind you, epsilon is a small quantity, so multiplying by epsilon makes the quantity smaller, okay, whereas 1 by epsilon is the zooming factor. So as you zoom closer, your spherical derivative is going to become smaller. Okay, that's what is happening. Okay, so for the zoom function, if the original functions have this bound M, then the zoomed functions have the bound epsilon M, and then because the zoomed functions the spherical derivatives of the zoomed functions converge normally to the spherical derivative of the limit function, which is the zoomed limit function, what it will tell you is that the limit function also, if you take its spherical derivative, is bounded by this epsilon times n. Okay. Now the point is that all this happens in this domain, which is the disk centered at the origin, radius rho by epsilon, right? And mind you, you must remember that as I make epsilon smaller and smaller and smaller, I am zooming closer and closer to the point z0, but then the zoomed functions are in larger and larger disks centered at the origin, because rho by epsilon becomes larger and larger as epsilon becomes smaller. Okay, so now the point is that you repeat this game, okay, by changing the zoom factor. Okay, so what you do is, instead of taking single epsilon, you take a sequence of epsilons which go to 0. Okay, a sequence of which go to 0, of course from the right, namely that you take sequence of positive epsilons that go to 0. Okay, so if you repeat the game with that, what you do is that now the nth function gn, okay, well, I think I haven't written it correctly the last time. The nth function gn is the zooming of the nth function fn by the factor 1 by epsilon n centered at z0 with the variable zeta. So there should have been an fn here, alright. So gn is the zooming of fn, alright, but the only thing is that now the zooming factor is also dependent on n. Okay, so fn is zoomed by a factor 1 by epsilon n, and I am calling it as gn. Okay, just what we did some time ago was keeping all these epsilon n's the same epsilon, but now I am making the epsilon n's smaller as n becomes larger. Okay, well, so if I do this, what happens is, mind you, if I make the epsilon n smaller, then the domains on which these zoom functions work, these domains become bigger. Okay, so so I get this, I get these domains. Okay, mod zeta lesser than, well, there was a, I think there was a rho, there was a rho there, mod zeta less than rho by epsilon n, and these are increasingly larger disks. As epsilon n goes to 0, these disks cover the whole plane. Okay, and in fact as n that means as n tends to infinity, you are getting you will cover the whole plane. In particular, you will cover any compact subset of the plane. So what you can say is that these zoom functions gn, you can talk about normal convergence on the whole plane. Okay, so actually what happens is that the anyway, as before, the fnks will converge to f. Okay, and therefore the fnk hash will converge to f hash, where hash denotes the spherical derivative, and then the corresponding zoom functions gnk hash will converge to g hash. All these convergences are all normal. Okay, but the only thing is that this, when you come to the zoom functions, this normal convergence is on all of C. It's on all on the whole complex plane, because now you've covered the whole complex plane. You've covered every compact subset of the complex plane by a sufficiently large disk centered at the origin, where that means all the GNs, all the GNKs beyond a certain k, they are all defined on any compact subset beyond a certain stage. Okay, so fine. So you have this, and the point is that the GNKs, if you take the spherical derivatives, they are bounded by epsilon nk times the bounds for the original functions, which is m. Okay, and therefore this limiting argument will tell you that the limit function g hash, the limit function g, if you take its spherical derivative, it has to be 0, and therefore you get a constant function on all of C. Okay, so you see the point is, therefore, as you go closer and closer and closer to a point and look at the zoomed functions, okay, then the zoomed functions they tend to become constant. That is what it means. Okay, the zoom functions become constant. So to sum up all this, all I am saying is that you take a normal family, you take a point where the family is normal, and then what happens is that as you take any sequence of in that family, you can always find a convergent subsequence if you study it at that point. Okay, then the zoom functions will they will tend to a constant function. That is the whole point. Okay, and Zalcman's lemma is all about being able to find zoom functions which converge to a non-constant meromorphic function. Okay, so something opposite to this happens. Okay, so what I want to do first is that I need to first of all tell you that I can repeat this argument with not just one point z0, but I can even take the sequence of points tending to z0. Okay, so now what we do is now take a sequence Ezn going to z0 in say the same disk mod z minus z0 less than or equal to rho, if you want. Okay, well, for that matter, if you take any Zn sequence Zn going to z0, the sequence beyond a certain stage will lie in that disk. Okay, but I am assuming this whole sequence lies in that closed disk centered at z0 radius rho. Okay, and what you do is now you zoom at each Zn. Okay, see, all this time we were zooming only at z0, but now what you do is you zoom at each Zn. So so you define Gn of zeta to be the zooming of, you zoom the function fn, but now centered at Zn, and the the zooming factor is 1 by epsilon n, and the new variable is zeta. So this means that Gn of zeta is it's fn of Ezn plus epsilon n times zeta. So this is the thing, but then I have to worry about one has to worry about where this will what about the domains of the Gns. Okay, you'll have to worry about that, but the point is that essentially as n tends to infinity, you're coming closer and closer to z0, so the domains of the Gns is going to again cover the whole complex plane. Okay, so one can write out the details for that. So the picture is like this. The picture is that so I have I have this z0, and there is the Zn, and then I have this so inside Z0 there is this big disk with radius rho, where I'm concentrating my attention, and of course even the boundary is included, though I am putting a dotted line. Well, and what I am doing is at Zn I am taking a I am taking a smaller disk radius epsilon n. Okay, and well, and then so Zn is tending to Z0, so well Zn plus 1 is closer to Z0 if you want, and there is it, and then I am taking a much smaller disk, and the radius of that disk is epsilon n plus 1. Okay, so I am taking smaller and smaller disks about points which are going closer and closer and closer to Z0. Okay, and the point is that on this I have this zoom function. Okay, and then if I go to Zn plus 1 I have another zoom function. It is Gn plus 1 of zeta, and this is Fn plus 1 centered at Zn plus 1. Yeah, so it's epsilon n plus 1 zeta. So this is just the zooming of Fn plus 1 centered at Zn plus 1 with the factor 1 by epsilon n plus 1 and the variable zeta. Okay, so I have these zoom functions. Okay, and Well, of course, I'll have to assume that the epsilon n's are chosen in such a way that the disk the disk centered at Zn radius epsilon n is within my big disk centered at Z0 with radius rho, okay, but that will happen eventually. Even if you didn't assume it, beyond a certain stage it has to happen, okay, but we assume, therefore, without loss of generality, that this happens. The diagram is like we have already shown it. So, for example, well, so if you take so I am assuming that if you take Z1, then I am taking the epsilon 1 that I am taking is such that the disk centered at Z1 radius epsilon 1 lies inside this big disk centered at Z0 radius rho, okay, and the point is that if this does not work, I can replace the epsilon i's by some epsilon I primes which I can calculate, okay. So the condition I want is that the distance of Z0 to any point of the disk should not be greater than rho, okay, it should be less than rho. That is the condition I want. So well, let us assume that the picture is like this, alright. We do the same calculations as before. You see Fn, you have this Fn k's, they converge normally to F, on normally, this is normally, and well, and what happens is that you will therefore get that the spherical derivatives will converge to F hash normally, and you will also get that the zoomed functions will also converge normally to G, and so will their spherical derivatives. Okay, so you will get all this as before. Mind you, the only thing now is that you also change the center of the zooming. Okay, the centers of the zoomings are all different now. Okay, but that doesn't change the calculation for the spherical derivative. Okay, because spherical derivative for the zoom functions is with respect to zeta, and as far as zeta is concerned, these Zn's are all constant. Okay, so well, again what you will get is that you will get that the original functions f and k, their spherical derivatives are bounded by m, and this will tell you that the zoom functions, their spherical derivatives are going to be bounded by epsilon, the corresponding scaling factor times m, I mean not scaling factor, the corresponding epsilon times m, and if you take a limit as n tends to infinity, you will get that the limit zoomed function, which is the zoomed function of the limit function, that will have a spherical derivative 0. Okay, that is because the epsilon n case tend to 0 and m is a fixed constant, positive constant, and the moment you and as before, the moment you know that the spherical derivative of meromorphic function is 0, it has to be constant. So this will tell you that g is constant on the complex plane. Mind you, this constant could have very well been the constant value infinity, that is allowed, okay, because we are in the context of meromorphic functions. But the whole point is now you've got this important characterization. You take a point Z0 where a family is normal, okay, then what happens is that you take any sequence of points Zn going to Z0 and you take a sequence of radii which are going to 0, the epsilon n's, okay, then given any sequence in the family you can find a subsequence such that if you take the subsequence and zoom it with respect to this sequence, the zoomed functions converge uniformly on compact subsets of C, that is normally on C, to a constant function. This is the behavior of a normal family at a point, okay, a normal family in the neighborhood of a point, okay, And the amazing thing is that the whole point is that this characterizes normal families. Okay, this is by this you can actually characterize normal families. Okay, so let me write this down, and the fact that you can characterize normal families like this is actually the philosophy behind Zalcman's lemma, and the way it works is it tells you when this is contradicted. So Zalcman's lemma will tell you that such a thing will not happen if the family is not normal. Okay, so let me write this. So proposition is, well, let script f be normal at Z0, which means that it is a normal family in an open disk containing Z0, and of course I am, all my families of functions are meromorphic. Okay, so let me write here normal family of meromorphic functions at Z0. Okay, given any sequence Zn tending to Z0 and any sequence of radii epsilon n tending to 0 plus, okay, for any sequence Fn in the family script f, okay, we can find a subsequence Fnk such that the zoomed sequence of Fnk with respect to Zn and epsilon n, that zoomed sequence converges to a constant function normally on all of the complex plane. Okay, G nk of zeta is equal to the zooming of Fnk with respect to center Zn Zk, radius 1 by scaling factor 1 by epsilon k, new variable zeta, which is by definition you just take Fnk of Ezk plus epsilon k times zeta. This is the zooming. Okay, now such that if this is the zoomed family, then G and K converges to a constant normally on the whole complex plane. So this is the characterization of this is how normal families behave. Okay, and the big deal about so this is normality at a point. Okay, this is normality at a point Z0, which means which by definition is normality in a small open disk containing Z0. That is what it means. Okay, and if you want to cover this to normality on a whole domain, then you have to say a family is normal on a domain if it is normal at each point of the domain. Okay, you can define it pointwise. So now let me state Zalcman's lemma, which will tell you and you will appreciate what it is all about. But with all this background that I have given you, you will see that Zalcman's lemma is something natural to expect. Okay, so here is Zalcman's lemma. And it's actually, well, it's called Zalcman's lemma, but it is actually a theorem. So what is the lemma? The lemma is about non-normality. Okay, see, I'll tell you in very short words. What we just saw is that if you have a normal family, then the zoomed functions go to a constant. Okay, Zalcman's lemma tells you that if you have a family which is not normal, you can get hold of a zoomed family of functions which will go to a non-constant meromorphic function. That is all, that is the whole point. Okay. So let me write that. Of course, you should always keep saying this in as little words as you can, so that you grab the main idea, but then of course when you write statements you will have to be, you have to bring in a lot of notation, you have to worry about a lot of notation, and then of course proofs are even more slightly complicated, but the point is that you should always be able to zoom out, and say things in just a few words, because that is how you will map it in your memory and remember it, and so that you do not lose track of the idea. Okay. So here is a lemma. Suppose script f is a family of meromorphic functions on a domain D, that is not normal. So here is a non-normal family. Then what happens is that there exists a sequence Zn converging to Z0 in D and epsilon n going to 0 plus with and further a sequence Fn in the family script f such that the zoomed functions Gn of zeta is equal to the zooming of the Fn's centered at the Zn's, scaling factor 1 by epsilon n, new variable zeta, namely Fn of Zn plus epsilon n zeta, converges normally on C to a non-constant, that is the whole point, to a non-constant meromorphic function G on the whole complex plane such that, okay, the fact that it is a non-constant meromorphic function, so you do not expect the derivative to be spherical derivative to be 0. So the spherical derivative at the origin will be 1 and all the spherical derivatives is bounded by 1. Okay. So this is Zalcman's lemma. So it tells you, see, it tells you that the behavior is exactly opposite to what you saw for a normal family. Okay. So we will try to prove this in the next lecture.